everybody. Happy to have you here once again on my channel. Last episode of this series, we read in the book How Linux Works by Brian Ward, the 3rd edition. And specifically we read Chapter 6, How User Space Starts. And I think I didn't quite finish it, but I got pretty far. I think at the time my idea was to finish the entire chapter in a separate, or finish the chapter in a separate video. But then I was like, well, maybe that's not such a good idea, because I don't want to put the entire book out there. If you want to actually learn something, you probably maybe should just buy the book. So that's why today we're doing a different chapter. I just opened the book up and I looked at, like, hey, what interests me? And that's what I'm going to read about, because otherwise I probably wouldn't be able to make a video like this. So today we're going to cover chapters 5, that goes over how the Linux kernel boots, and that is on page 117. So if you're following along, flip open your book to page 117, so we can learn about Linux kernels and how they boot. Actually, I don't know if there's a prior chapter about the kernel itself. Actually, I'm reading through the contents. I don't think there is. I think how the kernel boots is mostly about the kernel itself. Actually, no, I don't think so, because it's mostly talking about bootloaders, secure boot, and all that stuff. So, well, this isn't a very long chapter, but we'll see how far we get. Alright, let's get started. Chapter 5, How the Linux Kernel Boots. You know the physical and logical structure of a Linux system, what the kernel is, and how to work with processes. This chapter will teach you how the kernel starts or boots. In other words, you'll learn how the kernel moves into memory and what it does up to the point where the first user process starts. A simplified view of the boot process looks like this. The machine's BIOS, or boot firmware, loads and runs a bootloader. The bootloader finds the kernel image on disk, loads it into memory, and starts it. The kernel initializes the devices and its drivers. The kernel mounts the root file system. The kernel starts a program called init with a process ID of 1. This point is the user space start. Cool. Oh, and there's more. Init sets the rest of the system processes in motion. At some point, init starts a process allowing you to log in, usually at the end or near the end of the boot sequence. This chapter covers the first couple of stages, focusing on the bootloaders and kernel. Chapter 6 continues with the user space start by detailing System D, the most widespread version of init on Linux systems. Being able to identify each stage of the boot process will prove invaluable to you in fixing boot problems and understanding the system as a whole. However, the default behavior in many Linux distributions often makes it difficult, if not impossible, to identify the first few boot stages as they proceed, so you'll probably be able to get a good look only after you've completed and you log in. 5.1 Startup Messages. Traditional Unix systems produce many diagnostic messages upon boot that tell you about the boot process. The messages come first from the kernel and then from processes and initialization procedures that init starts. However, these messages aren't pretty or consistent, and in some cases, they aren't even very informative. In addition, hardware improvements have caused the kernel to start much faster than before. The messages flash by so quickly, it can be difficult to see what's happening. As a result, most current Linux distributions do their best to hide boot diagnostics with splash screens and other forms of filler to distract you while the system starts. The best way to view the kernel's boot and runtime diagnostics messages is needs to retrieve the journal for the kernel with the journalctl command. Running journalctl-k displays the messages from the current boot, but you can view previous boots with the -b option. We'll cover the journal in more detail in Chapter 7. If you don't have systemd, you can check for a log file, such as /var/log/kern.log, or run the dmessage command to view messages in the kernel ring buffer. Here's an example of what you can expect to see from the journalctl-k command. Then you just have the journalctl, obviously, the journal. I'm not going to read all this because it's just gibberish. I guess open up a Linux machine and type journalctl-k, and you'll see what I'm seeing, mostly. After the kernel has started, the user space startup procedure often generates messages. These messages will likely be more difficult to view and review because on most systems you won't find them in a single log file. Startup scripts are designed to send messages to the console that are erased after the boot process finishes. However, this isn't a problem on Linux systems because systemd captures diagnostic messages from startup and runtime that would normally go to the console. Kernel initialization and boot options. Upon startup, the Linux kernel initializes in this general order: CPU inspection, memory inspection, device bus discovery, auxiliary kernel subsystem setup, networking and the like, root file system mount, user space start. The first two steps aren't too remarkable, but when the kernel gets to devices, the question of dependencies arises. For example, the disk device drivers may depend on bus support and SCSI subsystem support, as you saw in Chapter 3. But then, later in the initialization process, the kernel must mount a root file system before starting init. In general, you won't have to worry about the dependencies, except that some necessary components may be loadable kernel modules rather than part of the main kernel. Some machines may need to load these kernel modules before their true root file system is mounted. We'll cover this problem and its initial RAM file system initrd workaround solutions in section 6.7. The kernel emits certain kinds of messages indicating that it's getting ready to start its first user process. Here, not only is the kernel cleaning up some unused memory, but it is also protecting its own data. If you're running a new enough kernel, you'll see the kernel start the first user base process as init. Later on, you should be able to see the root file system being mounted and systemd starting up, sending a few messages of its own to the kernel log. At this point, you definitely know that user space has started. 5.3 Kernel Parameters. When the Linux kernel starts, it receives a set of text-based kernel parameters containing a few additional system details. The parameters specify many different types of behavior, such as the amount of diagnostic output the kernel should produce, and device driver-specific options. You can view the parameters passed to your system's currently running kernel by looking at the /proc/cmd line or command line file. The parameters are either simple one-word flags, such as RO and quiet, or key equals value pairs, such as vt.handoff equals 1. Many of the parameters are unimportant, such as the splash flag for displaying a flash screen. But one that is critical is the root parameter. This is the location of the root file system. Without it, the kernel cannot properly perform the user space start. The root file system can be specified as a device file. As in this example, root equals /dev/sd1. On most contemporary systems, there are two alternatives that are more common. First, you might see a logical volume such as this. Root equals /dev/mapper/my-system-root. You may also see a UUID. Root equals UUID equals, and then a UID, obviously. I'm not going to say it because it's very long. Both these are preferable because they do not depend on a specific kernel device mapping. The row parameter, or RO parameter in instructs the kernel to mount the root file system in read-only mode upon user space start. This is normal. Read-only mode ensures that FSCK can check the root file system safely before trying to do anything serious. After the check, the boot up process remounts the root file system in read-write mode. Upon encountering a parameter that it doesn't understand, the Linux kernel saves that parameter. The kernel later passes the parameter to init when performing the user space kernel start. For example, if you add -s to the kernel parameters, the kernel passes the -s to the init program to indicate that it should start in single user mode. If you're interested in the basic boot parameters, the bootparam 7 manual page gives an overview. If you're looking for something very specific, you can check out kernelparams.txt or kernel-params.txt, a reference file that comes with the Linux kernel. With these basics covered, you should feel free to skip ahead to Chapter 6 to learn the specifics of user space start, the initial RAM disk, and the init program that the kernel runs as its first process. The remainder of this chapter details how the kernel loads into memory and starts, including how it gets its parameters. 5.4 Bootloaders. At the start of the boot process, before the kernel and init start, a bootloader program starts the kernel. The bootloader's job sounds simple. It loads the kernel into memory from somewhere on a disk, and then starts the kernel with a set of kernel parameters. However, this job is more complicated than it appears. To understand why, consider the question that the bootloader must answer. Where is the kernel? What kernel parameters should be passed to the kernel when it starts? The answers are typically that the kernel and its parameters are usually somewhere on the root file system. It may sound like the kernel parameters should be easy to find, but remember that the kernel itself is not yet running, and it's the kernel that usually traverses a file system to find the necessary files. Worse, the kernel device drivers normally used to access the disk are also unavailable. Think of this as a kind of chicken or egg problem. It can get even more complicated than this, but for now, let's see how a bootloader overcomes the obstacles of the drivers and file systems. A bootloader does need a driver to access the disk, but it's not the same one that the kernel uses. On PCs, bootloaders use the traditional basic input-output system, BIOS, or the newer Unified Extensible Firmware Interface, or UEFI, to access disks. Extensible Firmware Interface, or EFI, and UEFI will be discussed in more detail in section 5.8.2. Contemporary disk hardware includes firmware allowing the BIOS or UEFI, I'm saying that right, to access attached storage hardware via logical block addressing, or LBA. LBA is a universal, simple way to access data from any disk, but its performance is poor. This isn't a problem though, because bootloaders are often the only programs that must use this mode for disk access. After starting, the kernel has access to its own high-performance drivers. To determine if your system uses a BIOS or UEFI, To determine if your system uses a BIOS or UEFI, run EFI Boot Manager. If you get a list of boot targets, your system has UEFI. If instead you're told that the EFI variables aren't supported, your system uses a BIOS. Alternatively, you can check to see that /sys/firmware/EFI exists. If so, your system uses UEFI. Once the access to the disk's raw data has been resolved, the bootloader must do the work of locating the desired data on the file system. Most common bootloaders can read partition tables and have built-in support for read-only access to file systems. Thus, they can find and read files that they need to get the kernel into memory. This capability makes it far easier to dynamically configure and enhance the bootloader. Linux bootloaders have not always had this capability. Without it, configuring the bootloader was more difficult. In general, there's been a pattern of the kernel adding new features, especially in storage technology, followed by bootloaders adding separate, simplified versions of those features to compensate. 5.4 Bootloader Tasks. A Linux bootloader's core functionality includes the ability to do the following. Select from multiple kernels. Switch between sets of kernel parameters. Allow the user to manually override and edit kernel image names and parameters. For example, to enter single user mode. Provide support for booting other operating systems. Bootloaders have become considerably more advanced since the inception of the Linux kernel, with features such as command line history and menu systems, but a basic need has always been flexibility in kernel image and parameter selection. One surprising phenomenon is that some needs have actually diminished. For example, because you can perform an emergency or recovery boot from a USB storage device, you rarely have to worry about manually entering kernel parameters or going into a single user mode. Currently, bootloaders offer more power than ever, which can be particularly handy if you're building custom kernels or just want to tweak parameters. 5.4.2 Bootloader Overview. Here are the main bootloaders that you may encounter. Grub, a near universal standard on Linux systems with BIOS MBR and UEFI versions. Lilo, one of the first Linux bootloaders. eLilo is a UEFI version. SysLinux can be configured to run from many different kinds of file systems. LoadLin boots a kernel from MS-DOS. Systemd boot, a simple UEFI boot manager. Coreboot, formerly Linux BIOS, a high-performance replacement for the PC BIOS that can include a kernel. Linux kernel EFI stub, a kernel plugin for loading the kernel directly from a EFI/UEFI system partition, or ESP. EFI Linux, a UEFI bootloader intended to serve as a model and reference for other UEFI bootloaders. This book deals almost exclusively with Grub. The rationale behind using other bootloaders is that they're simpler to configure than Grub, they're faster, or they provide some other special purpose functionality. You can learn a lot about a bootloader by getting to boot a prompt where you can enter a kernel image and parameters. To do this, you need to know how to get to a boot prompt or menu. Unfortunately, this can sometimes be difficult to figure out because Linux distributions heavily customize bootloader behavior and appearance. It's usually impossible to tell just by watching the boot process which bootloader the distribution uses. The next section will tell you how to get a boot prompt in order to enter a kernel name and parameters. Once you're comfortable with that, you'll see how to configure and install a bootloader. And I think this is a fairly natural end to this video. Let's see how long we've been going for. A good 20 minutes. Okay, I'm fairly happy with that. I hope that was somewhat interesting to you. It was to me, at least. I didn't know half of the things that I read, so that's good. Yeah, thank you for watching. If you have any other topics you'd like me to cover, other books or other things related to technology, let me know in the comments and I'd be happy to do that. Probably. Obviously, no guarantees. If you like this video, don't forget to subscribe and like the video, obviously, because that helps me out. Tells me that people are actually watching this. So yeah, thank you, and I'll see you next time.